All right. So today we are talking about uh, radicals in chemistry and the basis of what it means to have a homolytic bond. So the big thing to know about radicals and everything like that is that we're not talking about the movement of two electrons. We're talking about the movement of one electron to both atoms in a molecule. Also, I'm joined by uh, Dr. Nicholas Morse today, who's he's a PhD in I think organic chemistry. Um, so he'll chime in if he has any ideas about what's going on. So with that in mind, let's just jump in. So what I want you to know is that a radical is an atom with at least one unpaired electron. Is an atom with an unpaired electron. So what do I mean by that? Well, a radical could be something like hydrogen by itself. So we're not talking about H plus, we're not talking about H minus, we're talking about H dot, all right, or the radical hydrogen, or simply the hydrogen atom, right? Because this is what hydrogen exists as. We can have something like the chlorine atom, all right? This is how chlorine exists in terms of its valence shell. We don't find chlorine in this way. It is a diatomic gas. So in other words, we usually find it bonded to another chlorine because it is more stable in its in having a full octet rather than this so close to being full octet. Same with hydrogen. Hydrogen is another diatomic gas. Going into more of the kind of away from the gen chem and more towards orgo, we have something called the methyl radical. All right. Once again, this is a methyl group, CH3, but that carbon does not have a full octet. It is close to having a full octet, but it does not. Other examples of things, and I don't know, maybe you'll see hanging around in, different textbooks, stuff like this. Um, this is nitrogen has a full octet, 2, 4, 6, 8, but this oxygen that's on top has the radical. This is called tempo. It's used for a few different reactions. Pretty out there. Um, if we wanted to take a look at examples of things that have, charges or, how does that work? So we can have something like the radical phenyl group. Um, this is possible. Uh, where we have the radical right there. So what we're essentially seeing is that once again is that the radical can show up anywhere and then it can participate in many different ways. Now, what I want you to know is that the radical can be written in a few different ways. So if I want to take this tempo molecule, for example, is there's nothing that's stopping me from taking it and writing it in a few different ways that it's possible. So, I can show the radical and all of the unpaired electrons, or I'm writing on the bottom layer. Shit. Or what I can do is I can take it and I can just write only the radical in terms of what I want to see. So again, this radical that's right there. And that makes it really clear to see where the radical is. Or again, just as valid is I can write none of it. And these all mean the same thing because you should know that oxygen makes two bonds and here it doesn't, so it must have a radical on it. So these are all valid ways of writing a molecule that has a radical on it. And so this brings into the idea of things like formal charge. Does a molecule with a radical, is it going to have a charge or not? And what we can say is that we can take the group number of the atom minus the number of unshared electrons minus the number of bonds. And this is a way of calculating what the charge will be of a molecule. This radical will show up as a 1 in here, where normally it will show up as a multiple of 2, like 2, 4, 6, or in this case, just one. All right. Uh, so the big thing to know about radicals is that, they show up in a few different places, and they're not necessarily this like big bad ugly thing that, like, yeah, it's an unshared electron, which is, don't get me wrong, really reactive. And, we're talking about atoms that are not at full octets, so once again, very reactive. But, these aren't things that we can only generate in the lab. So I'm sure you've heard about probably things like green tea or antioxidants or things like that, where in our body we have free radicals running rampant all the time. And it's free radicals in our body that lead to things like cancer or, cellular breakdown or, mutations going on, or over time our liver, if you drink a lot of alcohol, you have a lot of free radicals because of the peroxizymes in your liver. So, radicals exist everywhere. They don't necessarily just need to exist in the beaker. So with that in mind, let's talk about how do radicals form in our beaker, because that's what's, that's the thing we care about in organic chemistry. And then if you guys take something like biochemistry or biotechnology, you'll learn more about that, or, therapeutics. So what we're talking about here is the generation of radicals. And so the most important way of generating radicals is what we call the homolytic bond, okay? It's where we essentially take a bond, and what we're going to do is we're going to remove an electron, or we're going to give an electron to both of the atoms within the bond. And so what we have is we have H and X, the hydrogen and the halogen. And what we see is that both of them have received this one electron, the radical electron. And what I want you to notice that's part of this is that notice how the arrows have one hook, all right? One hook arrows tell us radical formation, all right? Versus if we saw something like this, I drew a nice arrow here. What we're talking about here is the movement of two electrons. And what we see going on is that we have these formal charges popping up, okay? And once again, you can go through and you can talk about the formal charges up above, and you can figure out, well, why does this happen? Use the formal charge formula that I gave you, and you'll see that this is why. So once again, that this is homolytic because each atom is receiving the same number of electrons, and this is heterolytic because the atoms within the bond are receiving different numbers of electrons, okay? There are a few different ways of generating electron or radicals that we use. Typical ones are things like peroxides. So, hydrogen peroxide, the thing you use to clean your wounds, stuff like that, or clean surfaces. This is a really good way of doing it. You can use something called allyl azyl propane, or I think it's just the allyl azyl part is what generates it. But in general, what we are going to be focusing mostly is radiation, okay? And we're going to look at how radiation is a way of generating radicals, all right? Later, we're going to talk about how radicals can be used in resonance, but we won't necessarily focus on that right now because generally I don't find teachers put a lot of emphasis on radical resonance. So we're going to kind of skip it, and we'll come back if we really care that much. All right. Where is my reference? All right. When we talk about the radical, we need to talk about how stable it is, because radical stability is what is more important than just knowing what kind of reactions generate radicals. All right, because it doesn't matter if we generate a radical, if it's so unstable that it makes things blow up, it's not important for us to know because we can't do anything with it. It's not useful. Yeah, it's a nice bit of trivia, but we don't necessarily care if we can't do anything with it. So what I will tell you, and what I've told you before, is that most organic radicals are really, really high in energy, right? You have an atom that is not at a full octet. And just like we learned in Gen Chem, being at a full octet is very stabilizing. So we find that radicals in general are just more unstable. And remember that if you are unstable, it means you are high in energy. So what we're going to find is that radicals in general are very high in energy species. And we're going to take a look at energy diagrams to talk about it. As always, just like how we talked about before in acidity trends, before, these same ideas of using resonance as a stabilizing factor is going to pop up, all right? And just like before, is that if you have the ability to have resonance, you are more stable because you're decreasing that effective charge that's going on the molecule. All right. So with that in mind, let's talk about bond dissociation energies. Bond dissociation energies, also known as the BDEs. Some teachers I find focus on this a lot, some don't. And because I don't know what your teacher is going to be like, I'm going to talk about it, but I'm going to go mid-level here. I'm not going to, go overboard talking about BDEs. A lot of times teachers, they want you to know like how they work. They don't necessarily care about the math, but we'll see. So if we have a bond of X and Y, all right, and we're doing a homolytic dissociation between X and Y, we know we're going to be left with X radical and Y radical. And what we can do is we can talk about the amount of energy associated with this dissociation of the bond. And so this would be characterized as the bond dissociation energy, which would be the amount of energy represented by enthalpy, that delta H, head back to your notes in Gen Chem, of creating the X radical. And to denote that we're talking about creating it, we're going to denote it with F for formation, plus the amount of energy associated with forming the Y radical. All right, so we can put a nice big old bracket around that. And what we can say is we're talking about the bond dissociation energy of formation of the reactants. Sorry, for the products. And what we can do is we can subtract out the amount of energy associated, the change in energy associated with forming X minus Y. Oh, not X minus Y, X bonded to Y, my bad. All right, so we're talking about the amount of energy you would get if you have stored within this XY bond. And of course, we can put brackets around this and we can call this the reactants. Bond dissociation of formation of the reactants. And essentially the equation we have going on here is that the product bond dissociation energy minus the reactant will give us the total energy change, okay? And so this total energy change can be represented as the bond dissociation energy. All right, so this is what we're talking about. We're talking about if we homolytically cleave the bond between X and Y, what kind of energy are we talking about in terms of X radical and Y radical versus the energy that was contained within the XY bond? All right. So if we wanted, we could talk about this. I'm only going to give one example of this. I'm really not going to go into super detail because I don't really think it's that important. But if we homolytically cleaved this bond between the H and the methyl group, and we took a look at some bond dissociation energies, and maybe, on the exam, your teacher will provide them to you and everything like that. But, what we're talking about here is the bond energy associated with the formation of the hydrogen radical, plus the energy associated with the formation of the methyl radical, minus the bond energy associated with the formation of just the regular methyl group. Right? Maybe you went up online, you looked up that this was 218 kilojoules, that this was 145.69 kilojoules. Maybe you looked up that this was negative 74.6 kilojoules. And what you find is that the overall amount is 438 kilojoules per mole. Great. So what are you telling me? Is that the bond energy associated with the regular bond as it's contained here is much higher than the bond energy associated with everything being separated. Okay? So what we're saying is that the bond as it stands, as it's together, is much more stable than if we were to keep it, otherwise. Okay? And so what I want you to know is that if we did the same thing as we started substituting out the carbon, the hydrogens on the carbon. So we have the methyl group versus the primary, so this would be 0. This is primary. Here we have the secondary. And finally, we did the tertiary. What I want you to know is that the bond energy associated in here with the bond that would get released is, what I should say, is that as we go up towards tertiary, we become more stable in terms of radical production, or that the generation of the radicals are more stable, okay? So that they're less in energy. So if you wanted, you could draw what the radicals look for every one of them, and you could say, well, all the hydrogen radicals are going to be the same, but all the alkyl radicals are going to be more stable as the radical carbon becomes more stable, okay? And this basically comes up with a rule for ourselves, is that in general, the more substituted the radical, is the more stable. And this is just a fact that's going to show up over and over and over again. More substituted, more stable. You're going to hear me saying that over and over and over again when we get to alkene chemistry, when we get to SN and E, tons and tons of different stuff. More substituted, more radical. It's right up there with the mantra of acids donate. So if you had to tattoo anything on your body, do acids donate first, and then more substituted, more stable. Again, we can talk about how resonance also factors into this, because what we can say is that if you have resonance, you are going to be increasing that stability as well. And so that stability is going to increase as we have resonance, okay? And I told you that we would talk about resonance, so I suppose this is a good time to do that. And so resonance, when we're talking about radicals, is, for all intents and purposes, pretty simple. We're talking about the same sort of ideas with radicals that we were talking about with just regular double bonds, with regular resonance. So, here I am cleaving the bond. And now I have this nice dot on the carbon, okay? In general, for what are called homoatoms, carbon and hydrogen, we have to show it because, if a carbon doesn't have any symbology on it, we just assume that it's full up on bonds. So if you have a carbon, you have to make sure you draw the radical. And then what I could say is that, okay, I know that this atom here, and this atom here all have extra electrons, okay? Or what I should say is delocalized electrons, or unshared. Can I say unshared paired? No, they're shared. But what they have going on here is they have electrons that can be moved around. And what we can see happen is that we can take one electron from this bond and this radical here, and what we could do is we can form a double bond there. And what that means is that the leftover electron here would move there. And what we have going on is we have essentially resonance, okay? And so it's this idea of resonance that's really going to produce stability. So this radical here would be wildly more stable than a radical that does not have resonance. Now you might be wondering, well, why can't this thing undergo resonance? The reason is because in order for this thing to homolytically cleave, it would have to cleave a CH bond, a full real bond. And we already know from looking at our bond dissociation energies that a bond like this is super stable. It's not going to destroy a stable bond in order to have a production of another one, unless if we can go up in the number of number of substituents. So what that basically is saying is that, you know, I drew this a little bit backwards, but what I'm trying to say here is that there is a potentiality of this homolytically cleaving and, you know, what this is going to form is a double bond here plus H radical, okay? And, you know, what I'm basically trying to get at here is that this double bond may be more stable. It may not be more stable. We don't know. We'd have to look at the bond dissociation energies. And this doesn't, you know, what I want you to be aware of is that, you know, there's a potential for this bond to, again, homolytically cleave. And here we are at a secondary radical, all right? And so this secondary radical is going to be more stable than the primary radical and may end up being what is formed overall, is basically what I'm trying to get at. Do we necessarily know that for sure? No, we don't. We can't say, you know, for certain that it's not. We can say that it's potentially favored, but this is the kind of thing that, depending on how into your teacher is about the bond dissociation energies, you know, we get into it. There's a great great PDF file I have. So if your teacher is like, oh yeah, you need to learn tons about bond dissociation energies, let me know. I can give you that PDF about what we're talking about. It's from Dr. Rubio at BU. He does an amazing job. Cool. So with that in mind, we have talked all the way about what radicals are, the stability of radicals, and all you really need to know is that more substituted, more stable, okay? Now, in terms of the radical stability, what we're gonna find is that when we react them, we tend to get a weird mixture of products going on. So what is the purpose of forming radicals? Well, radicals can be used in different reactions, which is shorthand for RXN, that generate pretty interesting molecules. So, you know, some of the ideas that we see going on here are things like, you know, here is here's fluorine, okay? And so, this is one of the things that, naturally exists. Actually, no, fluorine, I believe, is a anesthetic, all right? So you ever heard of diethyl ether? This is one of those things they produced and they can use them as an anesthetic. Um, the other things, like if you've ever heard of like chlorofluorocarbons, those are another thing that can be pretty fluorinated, or they have chlorines on them. And chlorofluorocarbons, CFLs, oh, can't remember, but those are the ones that eat the ozone. They used to use as what's it called, as refrigerants and stuff like that. Other things too, if you ever look at drug structures and you see lots of chlorines or fluorines or bromines in them, what we're talking about there is we're putting halogens. And so one of the ways of halogenating something is with these radical reactions. So with that in mind, let's just dive in. Okay. What I'm going to do is I'm going to give it to you in a way that is generalized, and then we'll talk about specific examples afterwards. So if we have just a regular alkane and we react this thing with a halogen, so we're talking about Cl2, Br2. We'll see in a second why we can't really use fluorine, even though I was talking about it. We'll show you in a second. You have to do it in a different way. And you're either going to be using heat, which we label with this delta, or you're going to be using light, which we label with the Planck constant HV, okay? So we're either talking about heat or light. And what we're going to see going on is that we're going to attach a halogen to the alkane, and the other halogen is going to pick up our nice hydrogen that's left over. So we have essentially a swap going on. And this is the reaction that we want to happen. And so by heating or irradiating the reaction mixture, what we find is that we can get this to produce the compound that we're looking for, okay? So if we had something like, I don't know, something like this, and we reacted it with Cl2, what we notice, and maybe we do this at 150 degrees Celsius, what we see going on is that, maybe we get the chlorine here. Maybe we get the chlorine there. Or even quite frankly, we might get the chlorine there. So we can get it in 3 different places, right? Because we can either have it at this carbon, or that carbon. And then what's of course left over is the HCl. Okay, so 3 possibilities. We can also react this with something like bromine. Maybe we have this compound going on. React it at 100, actually we'll react it in the presence of UV light. And what we're going to find is that we can get things like bromine there. We can get things like a bromine here. And then finally, we can get it on that primary. All right. And then, of course, we have the HBr left over for whichever one of these was produced. Here's the interesting thing, though. If we have chlorine, we do not produce the same equal measures, all right? So we have a mixture of products going on. For the halogens that form secondary for chlorine, so chlorine secondary halogens will probably produce at about 57%. All right, 57, 57, both of these 57%. Versus for this primary halogen, we get about 43%. So we have almost a 50-50% mixture, right? Not very selective, especially since, maybe this 50, collectively this is 57%. So maybe one of these is, half of 57 and, 25, 25, 43. But honestly, what we have is just a mixture of products, right? And what we see going on here down below is that for this tertiary bromine, it's 99%. Oh. So this primary one is, this primary one is about 1%. Actually, I mislabeled this a second. The formation of this secondary or tertiary product is 99%, with the tertiary being favored over the secondary, as we know, right? And we'll figure out why in a second, why that's true. And so what I want you to notice is the difference between these numbers. This primary chlorine is 43% versus this primary bromine is 1%. Well, what the fuck? Why? Why does this happen that we get such a disparity in products? Okay. The other question that I want you to kind of be aware of is, well, why are we only talking about chlorine and bromine? Where's fluorine and where's iodine, right? Because we're talking about halogens, right? And what I want you to know about fluorine and iodine is that fluorination of an alkane using something like F2 is wildly exothermic, okay? So what I mean by that is that when we react them together, we're going to generate so much heat from the reaction that it will explode. So if you try fluorinating a product using the radical halogenation method, you're going to blow up in the lab and you're going to cause problems. So even though we talked about above that having fluorines on is really common for pharmaceuticals or for different molecules, what we're going to discover is that we can't do it using the radical halogenation. What we will do is we'll use the Cl and Br. And the reason why we can't do iodine is because the formation of the H, basically what it is that if we look at the equilibrium going on between forming the Ri bond and the Hi bond, it so wildly favors the the unreacted products than the reacted products, that what happens is that as soon as you form this, it just immediately goes back. It would rather stay as the diatomic iodine than it would for the iodinated, the iodinated alkane. All right. If this makes sense, then you should be all set. If not, reach out to me. I can help you. I'll give you, an extra PowerPoint or a PDF. Again, Dr. Rubio does an amazing job explaining this, so I will pass you on his thing because he does a great job. All right. Let's talk about this reaction in terms of how we're supposed to do it. There are 3 stages to radical reactions. And it doesn't matter if you do chlorination or bromination, they are both the same 3 stages. The first stage is propagation. The second stage is, oh God. No, I did it wrong. Wow. Whoops. The first stage is initiation. Then we have propagation. And then we have termination. So this first stage initiation, what we're talking about here is we're talking about producing the chlorine radical that we're looking for in order to halogenate, or the bromine radical in order to halogenate. So if we have something like, propane, and we're reacting it with the Cl2 bond, and we're trying to generate, our mixture of products that we're talking about, The first step, initiation, is all about cleaving homolytically this bond between the chlorines. And what we're going to get is that we're going to get a chlorine radical that will go off and propagate the rest of the reaction, or essentially cause the rest of the chain reaction to happen. Okay. And so the reason why it starts off this way is because this chlorine bond is more readily able to homolytically cleave due to, chlorine is a big atom. So like we talked about, the acidity trends, big atoms, more stable. So this chlorine is able to handle the generation of the chlorine radical. Don't forget, we're talking about pretty unstable here, but what we're essentially saying is that this is a, at least favorable reaction at high energy situations. What I want you to know is that if we looked at the KEQ of this reaction, what we'd notice is that we have 3.63 times 10 to the negative 7th. Okay? This is wildly unfavored. Okay? Or what I guess the best way of saying it is that it's favored at high temperatures, but the concentrations of the two chlorine radicals is really, really low. So you could say that, for every, I think 13 chlorine radicals, we have about 1 billion unreacted Cl2 molecules. Okay. So this reaction lies heavily in this direction, even though we are able to generate a few of the, reactive chlorine radicals. What's important to know from this is that these chlorine radicals are going to immediately go off and enter into propagation. Okay? Propagation is all about generating the carbon radical that we need in order to cause the reaction to happen. Okay? So the chlorine radicals lack an octet because we, homolytically cleaved what's going on, and so that they're higher in energy. Okay? And so what can happen is that these chlorine radicals, they're hanging around with each other, and they could just so easily come together and just reform this bond, right? And which is what's happening in this equilibrium, is that that's just what they're doing. They're preferring to reform the bond. Or what can happen is that this radical chlorine could walk its way up to this alkane that's going on and be like, hey, bitch, I'm gonna steal your girl. And what we see going on is that we can form a alkyl radical. All right. And this alkyl radical is what is driving, the generation more, because for every chlorine radical that we scoop up, it's not turning back into Cl2. So we're slowly shifting the equilibrium this way. And so what this is going to do is it's going to generate more and more carbon radicals. And so what we see going on is we are slowly ramping up the speed of the reaction. So what's important to know is that we have, 3 possibilities for this propagation step. We can homolytically create a radical on this first carbon. We can homolytically create a radical on this middle carbon here. Should be yellow. And you should have radicals. Or we can create a radical on this last carbon on the left. And each one of these is perfectly valid. All right? They're all possible. Okay? What's interesting to know as well is that we can get a fourth radical where it's possible that when the chlorine comes up, that instead of taking one of the hydrogens that's hanging around, it just decides to be a bully and to create a bond with one of the carbons. So we have this carbon that I'm going to label in green over here. And that has a radical on it. Plus, we now have this ethyl group that's bonded onto this chlorine. So that's entirely possible. Now, if you go through and you look at the bond dissociation energies of what's going on, what we see is that thermodynamically, it's more feasible to steal a hydrogen. That's a much more accessible bond to break than this carbon bond, but I want you to know that it's possible, okay? So, you know, do you necessarily have to worry about the homolytic cleavage of a carbon-carbon bond? I wouldn't. Generally, we do these reactions mostly so that way we can talk about the hydrogen coming off, but we don't. We still have to say that it's a very, very possible thing to happen, okay? And so what I want you to notice about what's going on is that if we did the bond dissociation energies and we analyzed what's going on for this primary radical, what we find is that the amount of energy that we're talking about here is negative 11 kilojoules. And for the secondary radical, it's about the same. I think it's negative 108. Okay? So what's going on here is that we're talking about practically the same amount of energy, whether we're talking about a secondary radical or a primary radical. And this is why chlorine radicals generate pretty much 50-50 mixtures, all right? Is that their reactions are about the same in energy. So if your reactions are about the same in energy, then of course it's going to generate a pretty close mixture, which is how we get that almost 50-50 mixture of what we're talking about. Versus what I want you to see, and the important thing that's probably know about your exam, is that for bromine, if we just look at the two possibilities of secondary versus primary, so here's the primary one, here's the secondary one, is that for the primary radical, and of course we're talking about bromine now, for the primary radical, this has an energy of positive 71. Versus if we take a look at the secondary, this has an energy of negative 101. Oh, so that's why it's favored at 99% for that secondary radical. Because 99% versus 1%. Because if we look, this is non-spontaneous, it's endothermic, and that it requires that we add more energy to the reaction where the other one is spontaneous, okay? Or at least it's exothermic. I don't think we can say it's spontaneous. I don't think we can say that. It's definitely not spontaneous. What we can say, however, is that this is exothermic and favored. That's what we can say. So the generation of the secondary radical, which I didn't really draw correctly, is exothermic, and it's going to be more favored than the production of the primary radical. All right. What's the key takeaway of everything that we're essentially talking about here? What do I want you to know? What do you have to know for your exam? Most likely, all you have to know is that when we're talking about chlorination, radical chlorination with heat or light, you're going to get a mixture of secondary and tertiary products. Sorry, secondary and primary. Secondary and primary products. So in your exam, you're going to have to draw two things at least, okay? Versus when we talk about bromination, or radical bromination, I should say, using heat or light, what I want you to know is that, it's going to wildly favor tertiary first over its secondary counterpart, which I'm going to have to put another line there to show secondary. And then over its primary counterpart, which it's basically never going to choose. Okay? And so that's the basis of what we're talking about. This is everything that we just care about. And so when we're talking about the propagation, it's going to favor for bromine tertiary over secondary or primary. And then for secondary, for chlorine, it's pretty much going to be 50-50. All right. Well, this is all well and good, but we haven't gotten to the third step, right? We haven't even talked about termination. Step 3, termination. Well, we just did all this work to initiate the reaction to happen, and we did all this work to figure out, which radical is going to form on the alkane, but now we need to talk about, well, what happens when we need to end the reaction. And what we see is we have multiple different products. If I have this propane going on, then I know that this can be either the primary radical or it can be the secondary radical. If I'm talking about chlorine. If it's, for either one of these, for our termination reactions going on, is we could take this primary radical, react it with our leftover chlorine radical, because we generate 2 at a time, and then boom, we get the answer that we're looking for. So this is a totally valid reaction here. Primary chlorination. We could take our secondary radical that is favored to form, react it with the chlorine radical, and boom, we get the reaction that we're looking for. That's totally valid. What's also valid is a termination step is that we could just have 2 chlorines reacting with each other. That's totally fine. That's a termination. All right. And what termination is all about is that we're just getting rid of radicals. We're pairing them up. Okay. Propagation was, if you remember, was all about shifting who gets the radical. Okay. Because remember that each one of these ended up with an HCl. So instead of the chlorine having the radical, now the alkane does. But in termination, we're talking about matching up radicals together so they form a bond. So, here we're matching them up. Here we're matching them up. Here we're matching them up. But the issue with radical halogenation and why we don't tend to use it a lot is that sometimes we can just get the alkane groups to match up. And so now what's happening is that we're adding together 1, 2, 3, 4, 5, 6 carbons together, and we end up with a hexane. 1, 2, 3, 4, 5, 6. Whereas this is the new bond that was formed. Well, that's not great. What if we had 2 of our secondary ones hook up? Well, that's totally valid. That's a totally valid thing to happen. Boom. Or we could get a mixture of them. What if our primary one hooked up with our secondary one? What are we going to do then? Well, now we have our primary having a bond with our secondary. And these are all valid termination steps. These are all valid things to happen. All right. The the big important thing to know about termination is that we can't necessarily control what happens. All right. And so once again, if we took a look at our bromine, we can have generally a tertiary radical, or, you know, maybe if we're taking this molecule, then we don't have a secondary to choose over, but we'd have this primary radical. And so we can have the ability for these things to hook up, and so we get different, we get multiple different products going on. Okay. Here and here, this and this. And you can imagine what they would look like. All right. So, in terms of everything that we've talked about, is radical halogenation extremely useful? Probably not, because sometimes we get what we're looking for, but then just as likely we're going to get something we're not looking for. Okay. So, in terms of what we're discussing here, is that radical halogenation is a pretty wild reaction, I guess is the way of saying it. And the big thing to just know is that when we're talking about radical reactions, is that you're going to get a mixture of products, and you need to show as many are being asked for. So, like, what I mean by that is that generally teachers will be like, please show 3 valid products of the following reaction, or please show 5 valid products. All right. And, all products are valid, but they'll be in different concentrations. What's more to that is that your teacher might ask, show the primary and the secondary product. Okay. So in which case you have to go back to this idea about, well, what's favored for chlorine, what's favored for bromine, and make sure that you're showing what's it going to be. So for chlorine, once again, it's going to be about equal mixtures. And then for bromine, you're going to choose primary, or you're going to choose tertiary over secondary over primary. Okay. I didn't go a ton into thermodynamics and stuff like that in here, just because I don't find that many teachers necessarily go over it a ton. So, everything like that. I'm also going to skip, uh, NBS, the N-bromosuccinimide. This is another, instead of using chlorine, I believe, as a halogenator or as a propagation, we can use NBS. And another one that you could use is something like, I don't even know what it's called. I think NBS, or you could use like a peroxide, something like that. And we'll talk about peroxides later when we get to the alkene reactions. We'll talk about those. But I don't believe that we necessarily have to worry about those for this exam. However, I don't remember seeing it in the Northeastern textbook. So we'll go without it for now because it's not incredibly important. It doesn't necessarily show up in different places. All right. The big thing to know about radical reactions is the best thing to do is practice. So what I just want to show you is different ways that you can look up how to practice things. So you know, if ever you're like, oh, I really wish I had more radical halogenation practice, if you just try to look this up directly, you're going to get, you know, you're going to get like steps on how to do it. And this isn't necessarily what we're looking for, right? Like maybe you need an explanation, but for the most part, you just want things to practice with. What you should do is at the end, type in file type PDF, and this will bring up only practice problems for you. Okay. So here's all your practice problems. Here's more practice problems, different things like that. So tons and tons of different stuff. Use this in order. Another thing that you can do is instead of PDF, you can type in PPT for PowerPoint, and this will tell you, uh, you know, here's a PowerPoint on radical reactions, so you can, you know, open this and download it to learn more about what's going on. So like, here's another thing that was, all right. So, you know, here's another thing. Use this as you will. Cool. If you have any questions about what we went over today, let me know. I'm happy to discuss whatever needs to happen. For Northeastern students, tomorrow, Tuesday, 9/29, is going to be your midnight review. So please come with questions for that. And other than that, we should be all set. So goodbye.
Thank you.